Alright, so we have introduced the Chern class. Remember, the Chern class is a homology class to associate to a complex vector bundle on manifold. So if F bullet is a complex vector bundle, so in other words, a vect MC bundle on a manifold M, then we can associate to this bundle a class which is called the Chern class. So to associate it to this, we have the Chern class. And this is an element of the cohomology ring of M. By cohomology, we always mean the Chern cohomology. And this can be written or decomposed into its various degrees. So the 0 degree part is just 1. And then we have C1 of F plus high terms. So this one would be sitting in H2. So it's actually in the even part of the cohomology. So we have seen that, and in fact, this Chern class is associated to an invariant polynomial on the Lie algebra of the structure group GLNC. More concretely, so the Chern class is represented by the differential form, which is given as the determinant of the unit matrix plus the curvature form we normalize by 2 pi I, where omega is the curvature form of any connection on this bundle. Connection. Okay, and so this is this. So that's invariant polynomial. So it gives rise to this characteristic class by this general construction that we have discussed. Now, all characteristic classes have the property that they are natural. So if we look at a map F from another manifold N into M and pull back the bundle along F, then it turns out that, or for any characteristic class, we then have that pullback is compatible with the characteristic class. So if we compute the Chern class of the pullback bundle, which is a bundle over N, then that is the same thing as taking the Chern class of the original bundle, which is a cohomology class of M, and pull back this cohomology class. So we have that. That's called the naturality characteristic classes. So we have this for all characteristic classes. In particular, we have it for the Chern class. But the Chern class has some special properties that distinguish it from other characteristic classes, namely when it comes to the direct sum of bundles. So if you take the direct sum of two bundles, then this Chern class has the very nice property that the Chern classes multiply. So this is the cut product on cohomology, which is induced by the wedge product of differential forms. And this particular property comes from special properties of the determinant, namely that the determinant of a block diagonal matrix is the same as the product of the determinants. So this is this thing. Now there's one more property that I'd like to describe, namely you may wonder about the scaling factor on 2 pi I that I've used here. And one of the reasons for this factor is the following lemma. Namely, a priori, this is a complex polynomial, so it's a complex valued differential form. So we would have to write C here. Complex de Rham homology represented by complex valued forms. But actually, it turns out that the Chern form, or the Chern class, is real. So, the Chern class is real. So, meaning the Chern class of such a bundle is always sitting in the real Rham homology. It's not true that the representing form is always a real differential form. This is only true for special choices, but we can make the choices such that it's real, and therefore it represents a real Durand homology class. So why is that? Proof. And in order to see that, we equip our complex vector bundle with a Hermitian metric, and we, for the computation of the Chern class, then we use a Hermitian metric compatible connection. So equip our vector bundle with a Hermitian metric. So this turns it from a vect n C bundle to a Herm C bundle. This is always possible because locally you can certainly do that using a trivialization. Then you can use a partition of unity to paste them together. So that's a general construction that you'll probably have seen. So we can always equip a complex vector bundle with a Hermitian metric. And then we can also always find a compatible connection. So let Nabla be a compatible connection. So it's a connection of the bundle as a Herm M bundle rather than as a vect M bundle, right? So meaning it's compatible with this Hermitian connection, with this Hermitian metric. And then if we do the computation of the Chern class with respect to this connection, then the curvature and also the connection form take values in the corresponding Lie algebra of the structure group. So then the connection form applied to some tangent vector x, as well as the curvature form applied to two vectors. So they take values in the Lie algebra of the structure group, but if it's a Hermitian vector bundle, then the structure group is the unitary group, UN. So they take values in the Lie algebra UN. And what is that? Well, that is the set of all n by n matrices, complex n by n matrices, such that if you take the conjugate and the transpose, which is typically denoted like this, so the star means you transpose and you complex conjugate, then this is the negative of A. So that is the Lie algebra of the unitary group. Okay, so because that's always the case, right? So these forms always take their values in the Lie algebra of the structure group. And now, if we look at this form representing the Chern class, so let's do that. Determinant of identity matrix plus omega 2 pi I. So this is a mixed differential form, complex valued. So let's look at this conjugate complex conjugate. Let's see what happens. So if you have a matrix and you take the determinant, you take its complex conjugate. So then this is the same as taking the determinant of the complex conjugate of the matrix. So we have that. Now the identity matrix is the real matrix. So nothing changes here. And then we have this I factor here, which produces, when I take the conjugate, which produces a -1 here. So I get -1, and then I have the conjugate of the curvature matrix on 2 pi I. Okay. And now the determinant doesn't change when I transpose a matrix. So let's transpose it. And I have to transpose the identity matrix, which gives me the identity matrix again. And I have to transpose omega bar, which gives me omega star. So it's minus omega star on 2 pi I. And now I use the fact that I'm landing in this Lie algebra, which says that minus A star is equal to A. So minus omega star is equal to omega. So I get the determinant of the identity matrix plus omega on 2 pi I. And that is the same thing I started with, just without the conjugate. And so this tells me that this differential form here is a real value differential form that lies in A even with real coefficients, and therefore it represents a real de Rham class. But if you compute this representative with respect to a non-compatible connection, then in general it will be a complex form. It will still represent a real the cohomology class, but with this choice, even the representative is real, not just the de Rham cohomology. All right, so that is one thing. So this certainly now explains this factor of pi that I've used here to rescale my curvature matrix. This is what I want. This is because I wanted to make it real. And the 2 pi also has an explanation, but that's not something I'm going to prove here. Namely, actually more is true. In fact, this Chern class is not just a real valued cohomology class, it's actually an integral cohomology class. And so the Chern class is actually lies in the image, I should say, of the integral cohomology, where this is this is not defined in terms of the Rham cohomology. So, but you can then map this to integral to real cohomology by replacing integral coefficients by real coefficients, and so it lies in the image of this fact. And concretely, what this means is, so this means that if I pair the cohomology class with anything integral here, with an integral cycle, then I get an integer as a result. So this means that any of these Chern classes, let's say C of f, if I pair it with something, for example, with a compact oriented submanifold, let me write it like this first. I pair it, and this means I integrate a representative of this over this cycle, and I get something integer. And this holds for any smooth integral cycle, in particular for any closed, meaning compact and without boundary, for any closed oriented submanifold. Sigma in M. So if you take a k-dimensional submanifold and you look at the corresponding component of this of a representing cohomology class here, then the integration will give you an integer as a result. I'm not going to prove this here because if you want to actually prove it, you need to do a different construction of Chern classes in terms of singular cohomology, and then then compare the two constructions. And we will also not need that so but I just want to mention it. And that's the reason for this scaling factor 2 pi, because we want to make it integral. For our applications, you could also leave out this 2 pi and just work with it as a just ignore this factor. Okay, so that's not so important if you're not familiar with singular cohomology and what that means. You can also ignore this. Except for this statement, which makes sense in this. So that's the reason for this normalization. All right, good. And so that's one further property of the Chern class. And here is another one, proposition. think we did this already last time. The first one, namely, if my bundle F is trivial, then the Chern class is also trivial. Only this zeroth peak thing, which comes from the constant function, survives. So this is something I proved last time already. But building on this, we have the following: if F has rank n, so fiber dimension n, and k sections, globally defined sections, which are everywhere linearly independent, then some of the Chern classes must vanish, namely all those Chern classes must be zero for which J is larger than n minus k. So the more linearly independent, everywhere linearly independent sections you have, the more of these Chern classes must vanish. And this will, turning things around, this will tell us that if some of the Chern classes can be computed and turn out to be non-trivial, then not many of these sections can exist. So that's a measure of triviality of the bundle, if you will. So the more everywhere linearly independent sections you have, the more trivial the bundle is. At maximum, it could be k could be equal to n. Then you would have n sections which are everywhere linearly independent, then it would be just a trivial bundle. In case A, k equal n would just tell us it would be case A. So that would just tell us that k equal n would just tell us that the bundle is trivial, and then this would mean all Chern classes for J positive vanish. So then A is just a special case of B. Okay. Proof. So A has already been done 2 weeks ago. So we know already that if the bundle is trivial, the Chern class is trivial. And let's see how we can deduce B, this generalization from it. Well, so suppose we have these k sections which are everywhere linearly independent, then we can look at a subbundle of F, where in each fiber we look at the span of these k sections, which always will give me a k-dimensional subspace. So let S1 up to Sk be everywhere linearly independent. And now put Ex to be the subspace of Fx spanned by these things. So that is the span of S1 evaluated at X all the way up to Sk evaluated at X. That gives us a k-dimensional subspace, because of linearly independence, a k-dimensional subspace of Fx. For each x. So this way we get a new vector bundle, E, which is sitting inside my given vector bundle. Now this new vector bundle here is actually trivial. Namely, it's trivialized by these sections. E is a trivial vector bundle on M of rank k, okay? Because we have global sections for this bundle. Remember, a global frame is equivalent to having global trivialization. Okay, so we have that. And now, what we can do is we can choose a complement of E in F, for example, by equipping F with an Hermitian bundle and taking the orthogonal complement. So equip F with a Hermitian metric and put Gx equal to Ex per in Fx. So now we have a third vector bundle. It's also a subvector bundle of F. Right, then the construction is such that a given bundle F is the orthogonal complement of E and G. It's a direct sum of E and G. Alright. So otherwise, this is just a subspace and then it's orthogonal complement. And now we can do the computation. So the Chern class of F is the Chern class of the sum. Now we have this nice formula for Chern classes of sums. So that's the Chern class of E times the Chern class of G. But E is the trivial bundle, so this Chern class is equal to 1. It's trivial because E is the trivial bundle by A, by the special case A. And so what we get is that this is the same as the total Chern class of G. But now, what's the rank of G? The fiber dimension of G. It's of course the rank of the bundle F minus the rank of the bundle E. The F has rank N and E has rank K, so we have that. So that's the rank. Now, whenever you have any vector bundle, all Chern classes, so you have non-trivial Chern classes only all the way up to the rank of the bundle. So this is how we did the construction, right? So we took this thing. The maximal thing here is the determinant of the curvature matrix itself, which is of degree the rank of the bundle. So that's the highest occurring term. And so that means that for where is the statement? For j larger than n minus k, we have that the J's Chern class of F, which we have just seen, is the same as the J's Chern class of G, and this must then be 0 because then this J is larger than the rank of G. All right. So the more the trivial the bundle is, in the sense, the more sections that are everywhere linearly independent you have, the more of these Chern classes must vanish. So in that sense, the Chern class is a measure for the non-triviality of a bundle. Yes. The question was whether the converse is also true, that if these Chern classes vanish, if then we have these linearly independent sections, but that's not true. It works only in the direction as stated here. And in fact, you have partly seen this already in the exercises. Namely, this was one of the exercises to show that if a bundle is stably trivial, then the Chern class must already be trivial. And so that would be case A, special case A. But not every stably trivial bundle is trivial. And the Chern class wouldn't see that. Wouldn't see that it's not line enough to distinguish that. All right. Any further questions about this? Not at the moment. Then we should take a thorough look at an example. And the example that I want to study in some detail now is complex projective space. So the virtual audience can also ask questions. All right, and before we start looking at complex projective space, let me make a general remark on symplectic manifolds first. So, definition. Let M be a differentiable manifold of an even dimension, so let's say of dimension 2n. And then, what is a symplectic form? Yeah, a 2 form, little omega, a real 2 form. So this has nothing to do with the connection form. This is a 2 form, some 2 form, little omega, is called the symplectic form. Two conditions hold. Firstly, it must be closed. And secondly, it must be non-degenerate. There are various ways to formulate this. And so what I can do is I can take the n-fold wedge product so now omega is a 2 form, so the n-fold product is a 2n form, and this coincides with the dimension of the manifold. So it's this is a form of maximal degree, and I'm asking that this is never 0, nowhere on the manifold. So it's not equal to 0 everywhere on n. So what is the rank of the bundle in which this guy lives? That's a section of a certain vector bundle, namely the n-fold exterior product, or actually 2 n-fold exterior product. So what's the rank of that bundle? What's the freedom that I have in order to get this? It's 1, yes, exactly. So this maximal degree forms, this is of rank 1. And so, in fact, if I have that, then I have a rank 1 bundle, and this guy gives me a section on the whole manifold, which is nowhere vanishing. So in other words, this gives me a trivialization of that bundle, right? Okay. Anyway, so that's the definition, and that's a symplectic form, and this will be of some relevance for complex projective space, because that will be this sort. But maybe how can we see or check this condition if we are given a form omega, because going to some wedge product of high degree may result in a messy computation. So that's a remark here. In local coordinates, so if we write our form omega, let's say omega sum, it's a 2 form, so it looks something like this. If xi are our local coordinates, and it has some coefficient functions. And without loss of generality, I can assume that these coefficient functions are chosen symmetric. Because dx wedge dy is skew-symmetric. If you interchange dxi and dxj, you get a sign. So the symmetric part of this coefficient matrix will cancel out in the sum anyway. Right? So we need only consider coefficient matrices which are skew-symmetric. All right, and then if you look at this n-fold product here, so what you need to do, you need to do something like this. So you need to take this thing n times. Right? And I have to call these summation indices differently. So I have this, and now I have to expand the whole thing. And then I end up with a 2n form. But as we already said, this is one-dimensional, so there's actually in these coordinates only one 2n form of which we get. So that is form dx1 wedge dx2 wedge and so on, all the way up to dx2n. And so that says, if I expand this whole thing, I do the multiplication of all these things, then whenever I have an equal pair where the i's and the j's coincide in two of the sums, that will cancel. I only have to look at all those terms for which these pairs that I'm multiplying are pairwise different. And then up to order, they give me this term. And then I have to reshuffle everything to get this into this order. And the coefficient then will be something depending on the coefficient omega ij. Let me write it. Depending on this matrix omega ij. And it will be, of order n in this matrix, because these are n terms. So what is it? So this must be a scalar, right? So the omega ij is a matrix, and then I must end up with a scalar somehow computed out of this matrix omega ij. That's the first guess, right? The determinant is the first guess. But remember, omega ij is a 2n by 2n matrix. And this term is of order n in omega, and not 2n. So it cannot be the determinant. And of course, it was a trap, right? I asked you because I knew someone would say the determinant. But actually, it's what's called the Pfaffian. And if you don't know what the Pfaffian is of a skew-symmetric matrix, take this as a definition. We will come back to the Pfaffian later when we discuss the Euler form. But for now, we may just take this as the definition. So this is only defined for skew-symmetric matrices, but that's not a problem. I have assumed that the omegas are skew-symmetric. Okay? What we need to know simply, so we take this as a definition of this Pfaffian. It's not as well known as the determinant, but it's even more fundamental than the determinant in some sense, because in fact, what's true is this: if we take the Pfaffian of this matrix and we square it, then we get something of degree 2n. Now guess what's the result? Well, now we get the determinant. So the Pfaffian is a square root of the determinant, but it's not just some square root, it's a certain polynomial expression in the entries of the matrix, determined by this equation here. And what this tells us is this, namely, this coefficient here. So omega n is non-zero if and only if this coefficient is non-zero, right? But by this equation, that's the same as when saying that the determinant is non-zero. And that's the same as saying that the original matrix omega ij is invertible as maximal rank. So that would be another equivalent definition, or it would be to say that if I don't want to talk about the nth power of omega, I can characterize this condition in terms of omega itself by just looking at the coefficient matrix and demanding that the coefficient matrix is invertible. That's equivalent, as we have seen. So that's the only thing here that we need to believe for now. Good. Well, we'll come back to this. All right, so that's a symplectic form, and that's a characterization of this non-degeneracy condition here in local coordinates. And now, why am I telling you this? Yes, the dimension of it's a 2n, it's a 2n by 2n matrix. Well, you could make it, but then it would result in 0. Because if you have a skew-symmetric matrix on an odd-dimensional space, it's degenerate. So it would not be an interesting object to look at. Yes. Okay. And now, so let's see. Now the next thing I claim, so from now on, let me assume that M is compact and without boundary. So let M be closed now. And observe that this condition, that since this is non-zero, this induces an orientation on the manifold. Omega n non-zero induces an orientation, which is given by saying that omega to the n is positively oriented. Yeah. And it's non-zero, never zero, so I can do that. So it induces an orientation. So certainly M must be an orientable manifold if you want to find a symplectic form on it. All right, and with respect to this orientation, I can integrate omega n. And then I get, since this is never zero, so then I get something positive. It's the volume of the manifold with respect to this n, if I regard this as my volume. And the orientation, the induced orientation makes this positive. If I took the opposite orientation, I would get something negative. But I would never get something zero. All right, good. So I get that. And I've assumed that M is closed so that this integral converges. If M was a non-compact manifold, it may happen that this integral diverges. Then I could get infinite also as a result. If I allow that, that's fine. But let's skip to this. Let's stick to the closed case, and then there is no problem with integrating here. All right. Now I have a closed form. A closed form represents a cohomology class. Okay, and in fact, if I take any power of omega, so now what are the reasonable powers to look at? Well, k could lie between 0 and n. N is the maximal power, otherwise I have a degree higher than the dimension of the manifold. Well, 0 would be the constant function 1. K equal 1 would just be omega itself. And then I have all the other powers in between. And I'm claiming that this thing is also closed. Namely, if I apply the exterior differential to it, then let's get it out for a moment. So I have these k factors, and then there's this product rule for the exterior differential forms. And there are no signs popping up here because omega is of even degree. So I get d omega wedge omega and so on, plus omega wedge d omega wedge omega up, and so on, all the way up to hitting the last term is d But omega itself is supposed to be 0. So we'll always have one 0 factor in here. So we get 0. So the powers are also closed. Question: are they exact? Do they represent a trivial or a non-trivial cohomology class? And I'm claiming they are not exact. Why? Omega k is not exact for this range of k's. And why is that? Suppose it was omega k is equal to d of some eta. Then what we could do is this. We look at the maximal power. So omega to the n, which is omega k wedge omega n minus k. And here I now replace this by d of eta. Okay. But this way, but this is the same as d of eta wedge omega n minus k. But now there's a correction term by this Leibniz rule. So if I compute the d of this product here, I have one term where the d hits the eta. This is exactly that term that I have here. And then there's another term where d hits this part. So this has to be subtracted. But actually, eta is an odd form. And so when hitting this term, I get another sign. So I have to subtract something negative, which is why I have a plus here. But it doesn't matter anyway, because I know that this is 0. I know already that these powers of omega are closed. So what we get is d of eta wedge omega to the n minus k. And now if I integrate omega to the n over my manifold, I replace omega n by d. But I have assumed that the manifold is compact without boundary, so I can apply the Stokes theorem, and the boundary is empty. So this is Stokes. But this is empty, and so I get 0. But on the other hand, I get something positive. So it's a contradiction. So this is a contradiction to the assumption that the case power of omega is exact. So it's not exact. Okay, so all powers of my symplectic form are closed but not exact, so they represent a non-trivial cohomology class. So something which is non-trivial in the 2-case cohomology class. Cohomology group of my manifold. So you see, if you have a manifold, a closed manifold, and you want to find a symplectic form, you better first check the cohomology. All the even cohomologies, the even Betti numbers, must be non-trivial, otherwise no chance. Because we have these non-trivial cohomology classes in all even degrees. So that's a tautological obstruction to the existence of a symplectic form of a compact manifold. All right, good. And in fact, this is nothing but the cohomology class represented by omega to the case power in terms of the cup product, right? So this is the case cup product power of the cohomology class represented by the symplectic form itself. All right, very good. So that's a general remark. And now I want to come to projective space. A very little tiny remark in addition to this one. Remark. For a line bundle, so a vector bundle of rank 1, with a connection blah blah, the curvature form omega so the curvature form is defined with respect to a local trivialization, and it's defined on the subset of the manifold where you trivialize the bundle. However, in the case of a line bundle, what I'm saying is, in this case, the curvature form is globally defined. So it's an omega is a 2 form in your manifold with in general complex conditions. Why is that? In general, it's only locally defined, but I'm saying if the bundle has rank 1, it's globally defined. And one argument could be to say, well, omega, in the case, so is the bundle is of rank 1. So here we are talking about 1 by 1 matrices. And if you have a 1 by 1 matrix, then you have this. And trace is an invariant polynomial. And so whenever you apply an invariant polynomial to your curvature matrix, you get something globally defined. And of course, it's in a way a silly argument. So the real reason is this: if you have two different trivializations, so if T is the transition function for two trivializations, local trivializations. So that is a function defined on some part of the manifold, taking values in GL1. And then we know how the curvature matrices transpose. So you have a curvature form for one trivialization, a curvature form for the other trivialization, and then we have this this formula for the change of the matrix. But if this is one-dimensional matrices, in the case of one-dimensional matrices, these are just numbers and they commute. Of course, that would not work for matrices of larger size. And so that tells you that the curvature matrices, the curvature forms for two different local trivializations coincide on the overlap. So that's the way one should think of it. So even if the line bundle itself is not trivial, so that it cannot be globally trivialized, the curvature of 2 form is globally defined in the case of a line. Good. And now finally we can pass to complex projective space. So let's now look at n equals CPN. And first of all, I want to apply the symplectic stuff to this manifold. So I somehow have to construct a symplectic form. And there is a canonical symplectic form on this manifold. It's called the Kähler form, or I will call it the Fubini-Study form. And how can we deconstruct it? There are various ways to do it. I do it via a connection on a bundle. And so what is the bundle we are using? I want to come up with a globally defined form. So it would be good if it was a line bundle. And we have one outstanding line bundle on complex projective space, and that's not the trivial line bundle, it's the tautological line bundle. So and I want to denote this by tau, like tautological of CPN. Let this be the tautological line bundle on CPN. Okay, and well, if I give this line bundle a connection, then I automatically get a globally defined curvature. This is what I will take as my symplectic word. Okay, so what is the connection? How can we come up with a connection? Well, there's a natural choice. We can do this as follows. Remember that if this tautological line bundle is constructed as follows, so CPN consists, by definition, is the set of all one-dimensional subspaces of Cn plus 1. So if I have a point in this manifold, we call it L, then the corresponding fiber, or the corresponding fiber is just L. So that was the construction. So that is a one-dimensional subspace of Cn plus 1. All right. So that's the bundle, just to recollect. And now how can I come up with a connection? Well, the Cn plus 1 has its canonical Hermitian scalar product. And with respect to this canonical Hermitian scalar product, I can project from this space onto this sub-vector space. Let me denote this by pi L. So let pi L from Cn plus 1 onto L be the orthogonal projection. Yeah. And so the kernel of this projection is the orthogonal complement of L with respect to the standard scalar product on Cn plus 1. Respect to standard scalar product on Cn plus 1. Good. Alright, so and now the connection is as follows. So for the tangent vector to CPN at the point L and a local section S of tau. So what would be the result in differentiating this local section in direction x? That should be, again, an element in my tautological line bundle at L. Alright, so what can I do? I take this section, this local section. So locally, this associates to any point in the neighborhood of L an element in the corresponding line. So in particular, it's always an element in Cn plus 1. So I can consider this section also as a Cn plus 1 valued function on a neighborhood of L. Maybe to make this even more formally explicit, let me give this inclusion a map. Let me call this iota. Inclusion map. And then I can compose this with the inclusion map to make the point that now I want to consider this thing not as a section anymore of my tautological line bundle, but rather as a Cn plus 1 valued function on CPN plus 1, on CPF, or on a neighborhood of L in CPN. And now if I have a function, or a Cn plus valued function, I can take the usual derivative. I just differentiate every component of this Cn plus 1 valued function in the usual way. Then I get a new vector in Cn plus 1. But this new vector need not be an element of L. So there's no reason for that, but I can project back into it. This is why I want to use this projection here. So this gives me then an element in the correct fiber again. Okay, and so this defines a connection. It's easy to check that this defines a connection. So if you have, so it's certainly additive in X, it's additive in S clearly, everything's linear here. If you have a function on this X here, you can pull it up and pass it through this projection, no problem. If you have a function in front of the S, then you have to apply the Leibniz rule for the del S, which gives you a Leibniz rule for the connection. So it's clearly a connection, no problem. So that's a well-defined connection on the tautological line bundle. Good. And now we have its curvature form. And that's a globally defined 2 form on my manifold, right? So let omega in A2 of CPN and let coefficients be the curvature 2 form of this connection now. By the way, concerning this remark in the line bundle case. So in the line bundle case, I told you that this 2 form, this curvature 2 form, is a globally defined 2 form. How about the connection 1 form? Is this also a globally defined 1 form? Yes? The structure equation looks like this. How does this help? If we knew something about little omega, we could deduce something about capital omega from it, but now we try the occult, right? So we know that this is globally defined. Question is also this globally defined. I don't see that this helps. It's not like this. There's an additional term looking like this, right? dt times t to the minus 1. And this does, so this persists. Here you have a 2, and then you have a t. Here you have a 2. And this will in general be non-trivial. And so they will differ with respect to different. And what's really behind this is that omega, so curvature is a tensor, but a connection is not. Okay, that's just a side remark. Okay, good. Now we have this 2 form on complex projective space. Good. It's globally defined, we know that already. And also it's closed. That's also good, right? So d omega is closed, all curvature form is closed. So that's good for if I want to take this as my symplectic form. But it should also be a real form. And should be a real form. Omega is not real, but if I divide it by 2 pi I, or even only by I, that is a real form. And that's what we have just computed when we showed that that Chern classes are real. That is that gives me a real form. We will also do an explicit computation that confirms that. So that's good. So this gives me a closed real 2 form. And if I want to take this as my symplectic form, the only thing that remains to be done, we need to check that the maximal power vanishes nowhere, or that the coefficient matrix of this form, when written down in coordinates, is invertible. Right? This is what we discussed when we discussed symplectic forms. So this degeneracy, non-degeneracy condition needs to be checked. So let me denote this by little omega. This has now nothing to do with connection form. This little omega should remind us of a symplectic form, and the Fs stands for Fubini-Study. F is Fubini, and S is Study, because they were the inventors of a particular Riemannian metric on complex projective space, where this turns out to be the associated Kähler form. And very often in talks, you hear people mispronounce this name and call it study. This has nothing to do with study. It's a Studi. It's a German mathematician called Studi, after whom this is named. All right. Why is this close? Because we have this. Right? Whenever you apply an invariant polynomial to it, you get something close. We have proved that. In fact, the Bianchi, all these wedge product parts are zero. Right? So you have in the rank 1 case, you have that omega is given as the differential of the connection form minus, I always don't remember whether it's minus or plus, but in this case, this connection 1 form is just a scalar 1 form. So if you wedge it with itself, this gets 0 anyway, right? So you just have that. So in the rank 1 case, curvature depends linearly on the connection in this sense. This quadratic term disappears. And similarly for the Bianchi identity, this just tells you that the omega is 0. Yeah. So that's why it's a closed form. But I somehow like this argument. Could replace the trace by the determinant if you wish. Okay. It's also an invariant polynomial. Now, okay, so what we still need to do is to understand this thing to check that it's a non-degenerate, right? And how can we do that? Well, the non-degeneracy condition can be checked by looking at the coefficient matrix of the form, and that can be done in local coordinates. So let's look at this this form in local coordinates. Maybe that might be interesting to see anyway. Yeah, let's do that. So need to check this non-degeneracy condition that this is always non-zero. And we do this in local coordinates. Okay. So let's see. I'm looking. So we have this chart defined on a chart domain being diffeomorphic to Cn, which is as follows. So an element Z being Z1 all the way up to Zn gets mapped to some line. Each point here must get mapped to a line in Cn plus 1. And we have had a system of finitely many charts covering all of CPN by looking at the line which is spanned by the vector 1, Z1 all the way up to Zn, and where the 1 can also be at different places here. So if you take the 1 at each of the possible places, then you get n plus 1 charts, and they cover all of CPN. Let me just do it with this one, because it doesn't really matter. It's just a matter of notation where you put the indices. So this is a vector in Cn plus 1, and let's look at the line generated by it. So that would then be an element in CPN. Maybe we don't need that. Let's keep the formula for the connection for a moment. And okay, now in order to compute the curvature form in this chart, I need a local section defined on that chart with respect to which I compute the curvature, the connection form first. And so how would that look? So we fix tangent vector. So, and I will look at the following local section. S, which is defined only on this part of the projective space. And so in these coordinates, it's what do we have to do? Well, to each point in CPN or part of CPN given by the coordinate Z, I have to associate an element in the fiber of the tautological bundle over that point. But the fiber is just that point. So I have to associate to this point given by the coordinates Z. So I have to associate to that thing an element in that thing. That's a local section. What can I possibly take? Well, I just take this generator. That's the easiest thing I can think of. So that's a canonical local section that comes to my mind. So this is a local section which is nowhere vanishing because of this one here. It's not nowhere vanishing. So this gives me a local trivialization of the tautological bundle. And with respect to this section or local trivialization, I compute the connection 1 for it. In order to do that, I have to compute the covariant derivative of this local section at L and evaluate the result as a multiple of this section again. So I have to write this as S of L, and the coefficient that pops up is exactly the connection form applied to this tangent vector x. That's what I have. Now we can use this formula. So we get I L del x delta composed with S. So what is it? I L. Okay, so I have to look at this. Now I have to consider this as a Cn plus 1 valued function, and I have to take the usual derivative of it in the direction x. This one is constant, so it gets 0. And the other ones, I have to differentiate these complex coordinate functions in the direction x. So let me just write it like dz1 of x all the way up to dzn of x. Okay? So that's what I have. And now I need to perform this projection. So this is the orthogonal projection onto L. How do I get it? Well, I take the scalar product with a unit vector generating L and multiply with this unit vector. This is the formula that we know from linear algebra 2, maybe. From linear algebra 2 for orthogonal projections. So, okay, so we have the scalar product of this vector, like this. Well, let me just write it like 0 dz of x. And I have to take a unit vector generating the line. So I just take this vector normalized to unit length. So that would be the vector 1, z divided by its length, which is square root of 1 squared plus z squared, right? So that's the unit vector spanning that line times that unit vector. So that's the orthogonal projection. Good. And let's simplify this. So first of all, we get this square root times this squared, so this gives us 1 plus z squared in the denominator, and now here we have this scalar product. This gives 0 times 1 is 0, and then I have dz of x times z, but I have the scalar product is chosen such that it's anti-linear in the second argument. The whole thing must be linear in this argument because the projection is linear. So this must be linear component of the Hermitian product, so that is the anti-linear. This is why I get a z squared here. So if I take the scalar product, what we have is these coefficients squared times the corresponding coefficients here. Right. So that's what we have. This is the scalar product, and then times this vector. And now I have to compare it to the section. The section is exactly this vector. Right, so this is S. So I can compare coefficients, and I see that my connection form is given by this expression. Now I can raise the formula for the connection. So therefore, my connection one form with respect to this local trivialization is given by this expression. So it's the sum z square bar dzj divided by 1 on z. J is summed from 1 to n here. So that's my connection one form. Okay, that's good. That's not globally defined, but I know that its curvature is globally defined, so let's compute it and we do this with the structure equation. So omega is just the little omega, we simply have to apply the differential to it, and then we get a 2 form. And so what will we get? Alright, so we have two terms. One coming from the differential of the numerator and one of the denominator. So let's start with the numerator because that's a bit simpler. Then the denominator is unchanged. If I hit this with exterior derivative, I get a d here, and this doesn't give me anything because d squared is 0. So what we get here is sum over j, dzj bar wedge dzj. So that's the first thing. And then I get something coming from the derivative of the denominator. So that would be minus, then I have to square this denominator. Because 1 on something, they're differentiated, gives me 1 on something squared times minus the derivative of the something. So that would be, that's why I put the minus here. So then I have the derivative of that thing times this one. I'm messing up lower and upper indices. I hope you forgive me for that. And okay, so now the first term is as good as it stands. So let's just keep that. And the second term, well, if the differential hits the 1, this gives me nothing. So I can forget about this 1 here. And this z squared is nothing but z bar z. And if I hit the differential, then I get a dz and I get a dz bar. But when I get, when I get a dz and a dz bar. When I take the one with dz here, then I get dz bar times dz summed over j. That's exactly the same vector as here. So after wedging, this goes away. So the only thing that I have to look at is when the differential hits the z bar. Okay, so then we can rewrite this as sum over j. Then we have zjd, zj bar, which is the same thing with z and z bar interchanged. I hope you can still read this. So that's what we get. All right, okay. And in order to check this non-degeneracy condition, it may be good to express this in real coordinates now. So if you have these corresponding real coordinates, xj and yj are related to these complex coordinates in this obvious way. And then my omega becomes what? So let's look at this formula here. Okay, let me just insert it. Then we have this. Now if I hit this one with the differential, then I get dxj minus I dxyj wedge dxj plus I dyj. So that's the first term, that's this term, minus. And so here we have xj plus iyj dxj minus I dyj. And maybe I should call this second summation index differently if I wedge out everything. So I can call it k. Then I have the other term is summation over k xk minus iyk times dxk plus dy. And now let's, expand it. So dxj wedge dxj is 0. And similarly dyj wedge dyj is 0. Only the mixed terms survive. And so what we get is sum dxj times dyj, and there's a factor of I. And then we have minus I dyj wedge dxj, but if I interchange the dxj and dyj, I get back to this one, and the minus sign becomes plus 1, so I get 2 times this one. So that's the first thing. And the second contribution all right, so what do we get? This is summation over k. Then I get summation over j and k. Now, what? All right. We have xj, dxj, xk, dxk. That's one thing. We have xj minus I, xj dyj times xj dxj dxk. this times this, times this times this, this times this, times this times that. Right? No. Yes. Oh, this is a minus. It's a plus. No. No, sorry. I did this times that. So this was the one. This times that times this times this. And so there are lots of other terms. This is dxyj and dxk times d. Yeah. And well, so we have more terms plus this one xj d xj. Okay. Times I should make a note which terms I already have. So this times this I have, and this times this I have. So maybe the next one should be this times this, perhaps, yeah? I'm running out of time anyway, right? Yes. So lots of other terms. If you compute it, it turns out that all the real terms cancel out. And only the ones with the i's survive. Which confirms, and here's also a factor of I in front, this confirms the fact that if I divide by I get and this I can also write in terms of x and y like this. Minus, let me check. Formula that we get. I'm not going to spell this out. The easiest thing would do just split it into Sage and let it compute it. And now this is a positive function. So this is irrelevant for whether or not the thing is degenerate or not. And so maybe we should rewrite this as 1 or omega on 1 plus x squared plus y squared on I times omega. So this becomes a bit simpler. And also I can divide by the factor of 2 here. Then I have this form plus certain error terms. Now if you look at this, you see already, if I'm at the origin of my coordinate system, then all these terms vanish, because I always have some xj's or yj's in front as coefficients. Then in fact only this one survives. And so then in fact at the origin, this one is my form, and that's non-degenerate obviously. If you take the n, that's a standard symplectic form of Rn. If you take its nth power, you get the volume form of Rn, or 2n. So that's non-degenerate. So that tells you already, without any computation, that in a certain neighborhood of the origin, it must still be non-degenerate, because the invertibility is an open condition. So in a certain neighborhood of the origin, certainly everything is k. And we have just, the only thing that remains to be checked is that this is okay, not just in an open neighborhood of the origin, but on all of R, on all of Cn, on all of R2n. And if you sort the terms together and you apply a Cauchy-Schwarz inequality, then you see that it's invertible. Maybe I skip this part here. So straightforward computation gives you that this term is invertible. 1 and 2i omega is non-degenerate in the sense that I need for a differential for a symplectic form, degenerate. And It's a non-dependent real form, and therefore, if I rescale, then I just rescale by a positive real function. This is then, of course, also non-dependent. And this is the definition of my Fubini-Study form. So in other words, I do have a symplectic form on CPN. And by the general consideration on symplectic forms, we now know that the powers of the Fubini-Study form, so they give you a non-trivial homology class in degree 2k of CPN, real homology class of CPN. And next time I will explain why this generates that, why we have already discovered the complete homology of CPN. In fact, so in each even degree we have discovered a non-trivial homology class, and everything else is just multiples of this. So there is no further homology. We have found all the homology. This requires an additional argument which I will do on Thursday. And so I stop here for today. Thanks.